Okay, thanks a lot, Sharat and everybody. I think you can see my slides now. Yeah, I'm working at Tecnalia. It's in Spain, a research center, and I'm coordinating the robotics and automation teams over there. Okay, so Tecnalia, it's the largest applied research center in Spain. We are private, non-profit, and we actually work in all the main activities sectors, providing research and applying to companies. So we transform this technological research into prosperity for companies and for the society. In terms of robotics and automation, we cover a very wide spectrum of applications, as you can see in these different images. If you're more interested, you can Google Tecnalia robotics success stories on, and you have lots of YouTube videos that we publish every year, like a summary of some of the projects we did on every year. So we all in this webinar very aware that we need to do something if we want to keep life on this planet possible. We also are roboticists or interested in that, so we should be aware that our technology also has an impact, both because we create lots of electronic waste, and also because we use lots of energy for these robots to be active. So we're going to talk about efficiency, how to do stuff with robots, but the first thing we should do as a society is to focus on the sobriety. So do less and decide what we want to do with the budget that we have. If we want to budget of CO2 of activities that we have, if we want to keep the objective of 2 degrees. Okay, I think it's we don't hear it enough. We should also decide to not do things. Okay, when we decide to do things, we should do that better, more efficient. And here we have ideas about robots for environment, robots for green, and also how can we improve the robots by themselves. And these are 2 points that we're going to look at today. So when a few years ago I wanted to apply robotics to provide one more grain in the sand on that, I said where we should focus. And we decided to focus in Tecnalia on circular economy because as robots, it appears to be a good sector that we can do something. And also we can apply automation robotics to a sector that actually has an impact on CO2 and material extractions, about 20%. So of course, it's not enough. Of course, we need to change the energy sources. We need to go for electrification, stuff like that. But this robotics can't help on that. So circular economy is one of the possible entry points for us. Okay, so we had a look about what are the processes in this circular economy that robots could impact. And we launched different projects, different lines with EU funding at the moment. We have a few clients, but it's not very profitable, cleaning the environment, as mentioned, Charat, about removing plastics from the undersea, sorting the waste from the marine litter for the construction waste, other streams, stuff like that. We now work also on dismantling of electrical vehicles or of electronic components. And there's also a fourth line on inspection and repair. We can use robotics, 3D vision, artificial vision, 3D printing, stuff like that, so that we can repair and maintain and increment the life of the components. Today's webinar is not so much on this part, so I will skip it here. But I think it was important just to mention that robots can also be used to try to improve, let's say, the impact we have on the environment. Now, the other question is important is, could we do robots that impact less? Okay, we've seen the first presentation where they can propose polymers that can repair themselves, that can be recyclable. That's good. That's good. We had a talk just before in LCA. I will come back to this point at the end of my presentations. But if we talk that about more in engineering perspectives, robots, okay, it's not a major contributor to CO2. We don't move trucks around a lot, okay? But still, it's a complex electrical machine, and so we can try to improve them. We can take the part of the robot manufacturer And for that, apply eco design of the robots, just like any other machine, make them lighter, talk about design for maintenance, design for dismantling, so that we increase the lifespan of the machines, or we allow it to be easier dismantled and recycled. Monomaterial is very important in all these aspects, so that if you want to recycle, it's made of the same material, it's much better. An important point for manufacturers would be that they provide the ability to upgrade the robot after its first life. For example, in automotive plants, when the line is at the end of its life, the robots are still very powerful, very useful, but usually they're quite old. Not the robot itself, the control unit. And so you go to a KUKA, ABB, FANUC and say, okay, I'd like to keep the mechanics and just change the controller. That's a no-go, okay? So you need to scrap a nice robot just because the controller is too old. And of course, you need the advanced functions that are up to date. Talking about materials also, we should avoid using non-recyclable materials, just like the composites. We're all very fans of the KUKA EWA robots. Not so good because it's lots of composites. Not the only one. Lots of the cobots, lots of the compact, light robots for collaborative robotics. They include composites, so it's something that could be improved. And also maybe introduce biosourced materials, wood, things like that. Notice a research line. There are people in France working on that, how they can build wooden-based robots. If you need pointers, they are in Nantes, LS2N, and they're doing a great job there. Also, as robot manufacturer, we could think about the robot as a generator of electricity. When we brake or we decelerate during the motion of the robot, today, it's all going into thermal energy dissipation. And there's been a European project, FP7 Aarhus, with KUKA also, where they analyzed this dissipation. It was about 1/3 of the energy. And they introduced new electronics so that it could, the controller of the robot put energy back into the grid so that the other robots could use that. It's feasible, but the findings that they had in this project is that indeed it's a bit more difficult to integrate into the electrical scheme of the plant. And so it's as of for now, not something that they are pushing too much as manufacturers. We can also have an impact as users of robots or integrators, depending on which is exactly your position. And here again, in this project, KUKA, they worked a lot about where could I put AI into the design cycle of the robot. And they made an optimization of in this cell, which is a typical cell for welding automotive parts. If I actually optimize the placement of the base of the robots, doing exactly the same process, exactly the same cycle time, they can reach 30% energy reduction. So it's a bit of AI, it's a bit of time, it's a bit of optimization that has an impact also, but you get a 30% reduction of energy. And in that case, a peak power of about 50%. So also maybe you can use smaller robots, which also has smaller impacts. Okay, so it's a bit trying to look at exactly what you need and not just pick the one that looks the best. Optimization also not only on the base placement, but on the motion planning. So that's computation of the trajectories of the robot, the acceleration patterns, the actual motion that does the robot, which is the one that consumes the energy. Okay. And here, the findings that they had is also quite intuitive, no? Today, when we program a robot, we all like a lot to put it full speed, full velocity, full acceleration, and so on. And so we have a robot that goes very quickly to a point, but then he has to wait. Wait because there's a peripheral that needs to do something, or wait because there is a part that is coming, something like that. So we use the robots at maximum power, and then we wait. If we optimized also the scheduling of the tasks inside the cell, we would reach exactly the same timing so that we can operate the process of the robot but we would do that with much less energy. And so when they simulate that with also the partners on this project, these curves are the one they get, reducing a lot the peak and also reducing the overall energy consumption by again 35%. Looks like 1/3 is a nice number in our project, but that's quite interesting. And this has nothing to do with the hardware. So you keep the same cell, you just optimize what you do, when you do it, and how you do it. So it's 30% gain for everybody in the world. All these robots, they also use lots of AI that can include deep or reinforcement learning, like we see in this video from Google about optimization of a grasp, or at least learning how to grasp objects. But in all the applications that we do, or for recycling or for linear economy, for any robot now, we do a lot of agile and flexible robotics. We use a lot of motion planning. We use a lot of cameras, 3D sensors, optimal planning. This is daily basis, okay? We usually do that for a complexity of the application that require the robot to adapt itself. So that's positive for the deployment of robotics technologies in the companies and in the applications. But it requires lots of AI. That is not always deep learning. It can be some modules of deep learning, but not only. And since the last winter, sorry, we also saw a lot of ChatGPT everywhere. And now we also start to see ChatGPT to program the robot for us. So that's examples that were provided by Microsoft some month ago. We also do that in Tecnalia. We're also using this generative AI to actually ease the deployment of these activities. And that can be good because it lowers the entry level for people to program the robots to make more robotic applications. But well, it's ChatGPT. It's known to be a very, very energy-intensive training model. So it raises lots of questions. I'm actually thinking myself about what is my positioning on that. Might not be so positive, okay? So if you look at AI in general, it's very difficult to get numbers, to get information. That's the one I got. So you can use at digital, you can look at digital and you see that it's about 45% use during production of the digital hardware, let's say, and 55% use the generation of CO2 and impact in the two phases. When you look at training an AI model, like quite large one, it's like 5 times the CO2 emissions of an American car during its full lifetime. So it's not nothing, okay? And the thing is that the more we go with time, the more important the models. You have GPT-1, GPT-3. I don't know where is GPT-4. I don't know where is DALI and all these ones. Probably much higher on this curve where we see the training compute requirements, okay? So this translates directly to electricity, to energy. It translates also directly to hardware in the data centers. And the more the data centers go, the more we need GPUs and the more powerful GPUs and so on. So there's lots of turnover also in the hardware and the data centers. So basically, AI training is very, very consuming. It's very, very impacting. There's not real data about that, so it's difficult to know that. But we should all be aware of that and have a basic thinking. No, you have a standard algorithm that does the job. Do use this one. Don't use AI for that. And when you use AI, really try to use that or ChatGPT. I mean. If it solves relevant problems and not just to create memes on the web, that's funny, but it's really a very bad use of your CO2 quota that we should all have sometime soon. Also for the programming guys, it's interesting to think back also in the early years. I'm not that old, but I'm not so young now. We learned C, C++. We learned to optimize code. We learned to not just code as fast as we could. Because programming language, they also have an impact. And Python, that is widely used now, or Ruby, they are not so efficient. So also it would be interesting to put efficiency back into the training of the classes of programmers. So we started this discussion saying, okay, we should do less. And I'm talking all about AI, ChatGPT, robots, sensors, and so on. So one big question is that we should ask ourselves as users is it worth it? And it's not so easy to say, okay? So robots are used in many environments. They do have an impact. And how can we evaluate if this impact makes sense? Or can we compare these positive aspects that they bring with the CO2 emissions, with the impact on biodiversity, on the ecosystems, economic sustainability, and so on? So one tool to do that is the LCA, life cycle assessment, that we just had an introduction before. What I will do is take an example. In one of these projects, in this case, it's the sorting robot that we use in Maelstrom and Recomatic projects to sort marine litter and construction waste. We want to do this LCA. We have experts in Tecnalia to do that. So I'm the robotics expert. I'm not the LCA expert. So we worked together. They use software for that. The one we have is CIMA Pro, which is quite used a lot. And we see again this process of LCA where you need to define the goal and scope, the inventory, the impact assessment. You need to take all the steps of the use of your robot application in the life cycle and so on. And so when I take this example, basically, I'm a roboticist. I know where I put. So I have a Quattro robot from Omron. I have a near camera Red Eye 1.7. I have some lightnings, I have a belt, I have some motors. So this stuff, I know what I have. I have steels and paint, okay? But how do I put Omron Quattro robot within this inventory? The issue is that in this software, they ask you, in our case, we decided to put that in kilos, but they need you to have this inventory of basic materials so that you can use databases and they know the impact of bronze or reinforced steel with respect to injection steel, for example, okay? So the big issue for us, and the way I see a limitation in LCA, and that's something that should be improved, or maybe you have a community of LCA and robotics people doing a kind of, I don't know, catalog or something, is that we don't have the info. When you contact the robot manufacturers, you don't have the info. Nobody tells you nothing more than there is in the data sheet. And you don't even know where the basic materials of the robot come from. Is it built in China? Is it built in Europe? Is it built in the US? And so on. You don't know that. So it's very difficult to have a good LCA on that, or accurate LCA on that. Also, when you want to put that I'm doing AI deep learning training on the waste categories with a GPU of that category during 1 week in cloud from Amazon or from Google, that doesn't exist as a category. Okay, you have electronic sensors, so electronic components, not even sensors. Or if I take a mobile robot, we use a lot of LiDARs, 3D LiDARs. What is the difference between a 2D LiDAR and a 3D LiDAR? There's no way to know that. Okay, so I'm not saying that we should not do that. I really encourage everybody to start doing LCAs because just the process of doing it is very eye-opening, okay? What I think is that we need more education of researchers, engineers about these tools, about asking these questions. There's a lack of data from manufacturers, so how can we cover that? Should we do that as a community to create a I don't know, custom-based estimation of some commonly used robots and sensors? And also back into what the previous speaker was explaining, the LCA is also used in order to improve the product in early phases. And so helper tools here, I think that would be interesting to have so that at the beginning of the design, we have a rough idea of how good we go, how bad we go, and what we should improve. Today, it's quite cost intensive to make an LCA. And so it's a barrier for this early adoption. And again, using all this perspective, you should be able to decide if you want to go on with the project or not. We should, as humans, decide to stop doing things sometimes. So that was all for me. I hope it brought a different perspective to this community, to this webinar. and interested, we'll talk. And also you can join the EU Robotics Sustainable Robotics Topic Group. You got the website there. Thanks a lot, and back to you, Sharat.